All right, well, we're gonna attempt to record this with my phone now. So, hopefully this will turn out okay. All right, so last time we kind of did a big overview of what we're looking at. My assumption is at this point that most of you have seen some basic things of Verilog, but are not familiar with System Verilog. So I want to kind of go over some of the basic language constructs and some things that are unique inside of System Verilog, and why they're here, get you a little bit under the hood of what's going on with these. So we'll develop some of the guide rules for how we want to build logic and things of that sort. So I might have to check a couple times here to see where the edges of this are. How far can I go? Sorry to whoever's viewing this when you look at the movie. Looks like I've got a limit. I think that's about what I'm looking at.
Yeah, okay, settings.
Yeah, that looks fairly decent. Okay.
Where is that on settings?
So when you're trying to build something inside of Verilog, right? So we create a module, right? That module has some logic components inside of it. Let me ask you a question. What can I put inside of a module? What type of things do you standardly do inside there?
Inputs, outputs.
Okay. So under the module, I'm going to have inputs and outputs, which I'm just going to generally call ports.
I've got a.
Okay.
Privacy and security.
What else besides ports do I have?
Languages, download, printing, accessibility,
Use like
system, reset.
logic assignments, so you'll do like.
Okay, so I'll have various local declarations. What else?
Like the map portion, that's where you're like assigning the ports.
Yeah.
Okay, so what ways can I assign
Forward
ports?
slash, forward slash.
What way can I assign the logic? Could be local or ports or some combo. How can I do that?
Combination of logic.
What's that?
Combination of logic.
Okay, so
Dynamic
how do I declare a combination of logic? Okay, so those are kind of general ways of describing them. So I'm trying to get at what type of statements am I allowed to make those behavioral or descriptive or so on.
You can do like direct assignment,
When I do that, it automatically changes
Okay.
the block size.
So those assignment ones that are direct, we usually have the statement assign, and
You
then
can do it.
we'll say whatever it is, right? So
Do it
in particular,
aloud.
we call this continuous assignment, right? Because that one is gonna force whatever, and then you just have an expression, y equals whatever, or whatever the logical is that you want.
Yeah, it's something.
So I can have assign statements. What else can I use?
Use your initial block. and then module.
Okay, so there are initial, all right, anything else?
Right. Okay.
In test benches, you can use always, but it's not usually in.
All right, so always is the one that builds stuff. Initial sets up conditions, and is usually, it can occur in a synthesizable system, but it's usually only in a test bench. All right, we'll get into why on some of these. There's one other big group of thing I can do. Instantiate, right? I can instantiate other modules, right? This is kind of a big thing of what you're doing. Everything's going to get into one of these categories, right? Of the stuff that's synthesizable, typically you're looking here, here, and here. So let me start breaking some of these apart. Let me talk about what's going on with the initial and what's the difference between initial and always.
I'm working on it.
Right.
You have to type it in.
So initials, it's a block of code, and it's gonna run once and only once, right at the very start. That's what the actual name means. So this gets down to the concept of persistence, right? Always blocks have persistence. They continue to exist. Initial blocks do not have persistence. They do something and then they go away.
All right.
So this is why they're useful in test blocks, for instance. I can have an initial thread that could last the entire simulation, right? And I just keep putting time delays in them so that one run of it takes the entire time, right? And that allows me at definite time periods, or even according to some events, to give special conditions. I want to create an input. So this is how we can model what the rest of the universe is doing. Right? We can tell it to, for instance, wait 200 cycles. How can I tell it to wait 200 cycles?
Firefox, and all of them say the same thing.
Use hashes.
So it doesn't sound like it's a browser problem, it sounds like it's something
So-
to do with Canvas.
There's this lovely symbol. What does this do? Would that give me 200 cycles?
200 time
Okay.
units.
Right? So that gives me 200 of whatever your time units is, but that might not be a cycle, right?
It's crazy.
Can I do something like this?
What's a good one to test that?
Assuming I define cycle time.
Hey, what's a good?
Yes, I can do that. Right? Is there any other way I could get to do that?
Oh, you're just wanting to make sure it sees it.
You're talking about calling Verilog?
What's that?
Calling Verilog?
No, we're now talking some of the fun things I can do in System Verilog, but I could do more things than this inside regular
I
Verilog
was
too.
gonna test it in another.
But System Verilog adds some other fun stuff. Right? There are wait commands. I can even do things where I wait for a certain number of repetitions, so I could look for a pause edge. Right? And I could tell it to do 200 of those. Right? So there's a lot of different ways that you could go about them. But in any case, this would be one simple way to do them. But we can do things, so we can, tell any other command that you've got. So I've got the @ sign also. Right? So I can say, for instance, add a pause edge of the clock if I want to wait for the next cycle. So if there's a particular event, so I can use @ sign for event, hashtags for a displacement, right? I can tell it wait if you want. I want to wait till something happens. So there's a couple different versions, and I can obviously do multiples of these if I would like as well. Inside. So, but initials usually use these different types of timing parameters to specify when something's going to occur. So, I might want to wait for 200 cycles, and then the next positive edge of a clock, and I want to assert something. Right? So this combo would give me that type of functionality. So that's nice for handling, input sequence. The user waits a little time and then does something. That models the rest of the universe. I can do some things with an initial inside a realizable system because your system's going to boot. Right? So there are some realizable things where I might have some default things that are stored in some location, and I want to load those ones in.
And access the
Right?
camera.
Now, that's a simulation approximation. We'll talk about how you can actually force things to load in, but that can give you one way of approximating.
Okay, well, I have to leave at 3 o'clock, so that's why I was trying to solve this right.
Okay.
before I have to
How
leave.
about an always?
But,
Right? We said an always has, persistence. It's going to stick around. How does it work?
I got you. I just didn't know if there was anything else on here that we could look and see if it picks
Something
it up,
where
other than Skype
anytime,
that you
like you
do.
can say at the positive clock,
Okay.
something's gonna happen.
So there's some type of a trigger. There's an event.
Okay.
Think of this in terms of kind of event-driven programs or object situations. There's an event, so I have a sensitivity list that comes after this that tells me what am I going to be sensitive to, what events. Right? So let's say in my block that I say, at A. What does that mean?
Anytime A updates, you're gonna go through.
Yeah, if A updates, things like that, it's going to then go and it will run the code. So what if inside my always block I had something set up like C gets the value of A and B. Is that legitimate? Is that good? Will this work?
Yeah.
This actually will have a problem. It'll work sometimes and it'll fail at some weird stuff. And it will be very difficult to synthesize. What's the problem?
Well, there's nothing changing A,
What happens if B changes?
and nothing seasonally.
Shouldn't A and B respond to both A and B? This one will only update if A changes. All right? Now, you might mean that, but that's kind of a rather weird situation where you've got, in essence taking A and you're gonna have to somehow latch B to changes in A before piping it in, right? So you're looking at something like, here comes B in, and B is gonna have to be clocked off, A, and you're gonna need also a B clocked off not A. Alright? So I could actually just do that A or A bar, make my life easy. Alright? So I can do either one of these, and I'll get momentary little flips inside there, and then I'm gonna have to run that one out, and A comes in, and then they both go into an AND gate.
BAI.
Right? Because I gotta do some weird thing, I can only grab it at the edges. It's kinda ugly, right?
University.
We don't really like that. So that's probably not what you need. And when you go to actually build this, you will get some really weird things. You'll get some weird synthesis errors too.
Okay.
Sometimes it'll look like it's doing what you want, and sometimes it won't.
Support IP support.
Right? So this is a fairly common problem people had on early on, which was incomplete
Trying to
sensitivity
use
lists.
Canvas.
Verilog added something
The
to help you
problem
avoid that
we're
problem.
into is he's wanting to do a web.
Anybody know what they added?
And we have tried this in 3 different browsers, and every single
Star.
one of them. when
What
you
star
go
means
to
is
the
everything on the right-hand side.
It's saying that
So it'll go through for you,
Pages is
find
trying
everything
to
on the
say
right-hand
Adobe
side
Flash
and
is
put it there.
required. Adobe Flash is installed.
Shouldn't I have everything on both
Enabled,
sides?
And made sure that we added an exception to whatever
No,
it
you're
is.
correct, I shouldn't. Why shouldn't I?
To
Why
ensure
is the
it's
left-hand
100%
side
enabled
irrelevant?
For
Because
the
that's
particular site.
what we're looking for.
And
That's what
it
we're
doesn't
building,
matter what
right?
we do,
Yeah.
it keeps
So,
saying
but
you
it
need
doesn't
Adobe
feed on the
Flash,
other
you
side.
need Adobe Flash.
And if it did, it would be on the
Basically,
right-hand
we're kinda
side.
stuck
The
with
right-hand
this.
side are
No
your
matter what-
inputs, that's your
what browser
outputs.
that we look at.
So I only need to handle my simulations and updates when something changes on the input side. Alright, so that's for my always at star. What type of things, when I do always at star, what should Verilog build? What type of circuit? Generally, this builds what's called combinational logic.
So I don't know.
Alright?
I mean, I could
Now
probably
notice I'm being
try.
very careful with my wording. Generally, it builds combinational logic.
So the one.
When would it not?
Let's see. Pulls up here.
I guess when combinational logic is used.
It is 2018, or 201830 ELC 439601.
Let's actually just leave it there. Alright?
Okay, so he's gone to my.
Is this legal code?
And then at my media, when it brings up the
Yes.
list on there, then he.
Right.
Add new,
Oh,
and then click on webcam recording.
if
As
statements,
soon as he does,
perfectly legitimate.
box
We know what if
pops up.
statements build.
Page at HTTPS.
How about this? Well, let me ask you first, what does an if statement make?
The whole address. .com says, sorry, this action requires.
What's that?
Condition?
Okay, how do I build it physically?
A mux.
A mux, right? In this case, I've got two things, an if and an else. Right? So it's gonna build a mux. And I'm saying if B is greater than 0. So I'd have to have a comparator circuit, which checks greater than.
Well.
And I put B here, and I put 0 on its input, and it gives me an answer, is B greater than 0, and it runs it in here.
I mean, usually
Right.
it uses Chrome.
And if that's true, i.e. I get a 1 output, then I want A and B logically ANDed together. I'll do IEEE's format instead of the standard gate notation just for simplicity here. All right?
Yes.
And this is my output C. That's what I've written. Do you see what the problem is?
Oh, okay.
This looks like, and it's perfectly legitimate Verilog.
Defaulted it to
There's nothing wrong with this Verilog code. But do you see, I haven't fully described everything.
reloading.
All the options aren't there. The if statement, I haven't said what to put if it's not. I've told you what to do if it is.
And voila.
So implicitly, what should it do if it doesn't know what else to do? Right? I could set it to 0, that'd be one thing. What else?
Leave it where it was last.
Leave it alone.
Okay, well, that's
Right.
simple enough.
Which one seems to make the most sense? Generally, what do we want?
For your help. I think
That is what it usually assumes, which means it's got to do that. But it doesn't have any timing. It doesn't have a pause edge or anything else. So what does it have to do? It has to put a latch in. Right?
Turned out it was just the way that Flash is configured on there.
So it'll work next time I do it?
If you have that problem again, where it says secure right here, because it is HTTPS,
Okay.
you can click on it, and it was the default for Flash, you can see here, is block. So you can just change it to allow,
Awesome.
and then when I did that, it let me right in.
Woohoo. Well, now we'll be able to do this easier. Hopefully my phone is still working well, and we'll get a
Sorry
legitimate.
it took so long, but.
Yeah, it still seems to be happy, so. All right. So the problem is that it has a latch, so it's inferring memory, right? Anything that has memory, even a latch, is not technically a combinational circuit. So this @ sign, while it should imply combinational logic, it can also end up giving you memory elements, and very weird, badly timed memory elements, which can cause metastability in your circuits and all kinds of other things. And you don't always want to imply memory where you didn't. Maybe you just forgot. Maybe you were supposed to put a default case in and you forgot to put the default case in. All right? So what we would like to be able to do is to be able to specify something that handles this. Yes, I don't want to write out the sensitivity list for standard combinational stuff, but that also prevents this stupid latch creation. So if you've ever got an error message that says something about a latch or something inside there, this is what's happening. This, or it happens in case statements, it happens in a bunch of different areas, where part of the circuit is not actually known, right? But it's legitimate. You wrote legitimate code, you just didn't give it enough to specify a realizable system. And as a result, it had to infer something that implied memory. And since it doesn't know timing, it creates latches instead of flip-flops. So that's the problem. Well, so this is where System Verilog comes to your rescue. Underscore comb, combinational logic. It automatically creates a sensitivity list of the right-hand side, and it will not build this. It will flag you an error and tell you that you have an incomplete system. You didn't specify all your cases, which is actually a somewhat useful debugging notation. So you look at that and you go, oh, I didn't create all my conditions, and then I can fix it. Right? And I can either, what are the ways I could fix this one?
I have an else.
I could put an else and I could specify. What else could I do?
Put a clause.
Right? Well, I do want combinational.
The default.
I could put a default, right? I'd have to do a begin end, but I could say C equals whatever. Right? And then on these cases, it would overwrite it. But then I told it, in every case, C should be this, but in these special cases, do this different thing. Right? So I could say, begin C equals 0. And then if B is greater than 0, C is equal to this. Right? And then it knows if B is not greater than 0, then C is equal to 0. There we go. Does that make sense? So we're going to start using this instead, because now you can state exactly what you want and you can avoid all these latching errors. What we're trying to do is to be able to directly state what is your design intent. Okay? Is there anything else I could do with one of these always blocks?
They're commonly used to create registers.
Right? So that's the other way I could go. How do I, is it okay if I erase this? And if you notice there, when I wrote those, I immediately knew what the circuit was. I want you to get comfy with that, right? You should, when you write your code, you should be able to see your circuit or draw your circuit, right? Because that's the only way you can make sure that it's building what you want it to build. So if when you're writing your code, you don't just think, can I write code? You think, what is it building? That's what's going to guarantee that you've written good, solid, synthesizable systems. How do I tell it that it's going to be a system with memory?
We use reg variables instead of wire.
So does reg always mean it'll get memory?
Not always, just means that you can use it in an always.
Right? Yeah, I have to do them inside. So that's even true with the always hat star. Right? So I'm going to defer. There's actually some interesting things about wire and reg that are changing here also. Right? Well, I'll tip the hat and I'll explain it later. These are both going away from our purposes. They still exist, but you won't use them anymore. Right? In their place, we get one thing, logic. And it will figure out whether it should be a wire or whether it should be a reg all on its own. Right? So this actually makes your life a little bit easier and implies the correct type. So you could actually use them in different ways. But let's get back to this one. What's the way that uniquely tells? What do you need to know in addition? Like if I said like always, and let's say I want to make just a simple flip-flop. So I could say, if, let's say clock is equal to 1, then let's say D gets the value, so Q gets the value, we wrote that backwards. Q gets D. Is that legitimate code? So what have I built?
It's not faithful.
What is this?
It's also a dash.
It's a latch, right? So what makes this a latch?
It's operating on the high level instead of the edge.
Okay, so what if I did something like this? Pause edge, clock. it should get a flip-flop, right? But it'll still have actually some issues on this because I haven't told it what to pay attention to. And so the usual thing you have to do to make sure it knows is to give it watch for the positive edge of the clock. Right? That sensitivity list, it looks at that and says, oh, I'm an edge-triggered flip-flop. So that's one of the key things it gets. But sometimes I do want the latch. So what they actually do for you is they create two different always when I go to system Verilog. There's always underscore latch, and there's always underscore flip-flop. So this one specifies your exact design intent.
Can you give examples of when you would want one and not or the other?
So in general, you probably want a flip-flop. I'll just make that as a general statement. Flip-flops are edge-triggered. And so therefore they occur at specific spots. So when we're building these, there are flip-flops that are built inside. This is kind of like your standard D register cells and things of that sort. And that's what allows us to avoid what we talked about last time, the errors of type 1 and things of that sort. We had to know exactly when we were looking at stuff, right? So you can imagine, it's just like if I were to film a movie, right? I would get a series of picture shots. And I want to make sure when those picture shots, things are good. What happens technically in between those picture shots, and it's, you know, maybe 1/70th a second, technically doesn't appear to me, right? But as long as it's good for that little snapshot, that's all I care about. So for us, if my signal is mostly good, but it's got some glitches that occur that I don't want to have happen, right? This is 1 and 0 is way down. I actually probably got a frame there. Right. This is the 1 value and the 0 value, and I get these little glitches every now and then, right, on my signal. But if when my clock is coming in, it's only measuring here, so it never sees the glitch, it could be a perfectly smooth flat line as far as I know. Okay? And that's what we're going to rely on. So in general, you typically want a flip-flop, both for those error type of conditions. When we're going between different clocking regimes, flip-flops are going to allow you to control, you know, it won't allow problems to go through. So it's, you know, typically you can put 1, 2, sometimes a few more flip-flops, and you can handle almost any amount of uncertainty or ambiguity that's going to come with metastability. And you can fix them by putting layers of flip-flops. We'll talk about that in more detail later, right? But it's one of our great ways of fixing those type of problems, to be able to synchronize to our system, and then we don't have to worry about them. And it removes a lot of those problems.
So with the always flip-flop notation, I know.
Always underscore flip-flop,
Yeah.
FF.
I know with just Verilog with the always at positive clock, we usually also add the or reset or positive reset.
Yeah, so this is a sensitivity list.
Mm-hmm.
So, and just like before, you have the same option, so I can still say pos edge of clock, right? And I can, usually you can do the or. I don't advise using the or symbol,
Okay.
right? And so the or symbol is Verilog 95. Right? And technically what they did is they took all of the things and they OR'd them, and if a 1 came out, then it ran. Okay, that's great as long as you're not doing negative logic. Right? So there are some cases where the OR doesn't actually make sense. Okay? So if you do the comma, it's just telling you, I'm going to give you a list of things I care about, and if anything happens in any of them, let me know. Right? And so now I make the machine handle all cases for me so I don't have to get into the tedium. And I could go in and do the tedium myself, but human beings stink at tedium. Right? If I give you a very menial task, there's a high likelihood you're going to make a mistake. Right? The more menial a task I get, even with I mean, heck, at this point, I'm over 3 decades doing this stuff, right? But the more menial a task I get, the higher likelihood I make an error. The more challenging the task, the less likelihood I make an error. Right? It's kind of sad but true, but I mean, imagine if somebody were to go back and just ask you to add 100 numbers. The likelihood of you just adding 100 numbers any better than a typical person on the street is pretty low. Right? Now, a computer which has no intelligence whatsoever can do that all day long. Right? We don't deal with low-level stuff. But if I give you something that really challenges your mind, you're going to think about it, you're going to figure it out, and you're going to solve it. More challenging things you will work at till you beat. Right? So computers deal with tedium, we do not. So make them deal with tedium. So the comma was introduced in the 2001 standards in Verilog, and it's been kept on since then. So then we can also say, like, you know, we want neg edge of reset. Right. And you can technically have as many things as you want inside that sensitivity list. The big thing to get, though, is that sensitivity list, you know, from here, we often look and we go, oh, you got positive and negative edges, it must be a flip-flop that you're doing. And that's a fairly good way of assuming them, but, you know, it is possible that I could be doing something weird that signal mattered and I wasn't trying to infer memory. So it's nice to just say, what was your intent? Did you want combinational logic? Right? No memory. Did you want a latch? Anytime the latching signal is asserted, it will copy it over. So it's continuous when its clock input is high. Right? Or did you want a flip-flop? It only triggers on an edge. And in general, your best designs are these two. When memory can change over an entire region, it can get ugly. Right? The reason why you'll often want to do latches, if you do them, is if there is a combinational circuit and you're just trying to hold a value for an intermediate. But it's a short duration type of a thing. Right? So you only need to use it if some error flag kicks up or something like that. And it could happen at any point. It's not guaranteed to occur on an edge. You know, latches make sense. But I would generally say use these two, and if you have a reason to do a latch, then do a latch, would be my advice. Make sense so far? Okay. So, that's the same thing. Sensitivity lists still exist for all of these. Just realize you don't have to put them in. You should put them in for the flip-flops, for the triggered ones. But anything on the right side for these ones is going to happen automatically. So it will try to infer from other stuff because it knows what you want it to do.
What's the difference between happening automatically and putting the star?
So technically for the star one on this one, there's no difference from star and having it automatically list. That's what star does. The difference that comes in by doing this is that it will rule this case out. Because when you do the star could apply to either of these. Star cannot apply to this. Right? Because this, you only want it to be sensitive to certain things. You do want it to ignore signals. Right? So star does not make sense for a flip-flop. But star does make sense for combination or latches. So this is kind of the problem. The star case covered two, and we needed to specify. Make sense? Okay. So let's get into one other kind of fun thing that happens in these, right? Assignments. What does this mean?
Simultaneous.
Yeah, we call it non-blocking. Right? It means all the lines technically go at the same exact time. Right? So this one is called non-blocking. Actually, I'm gonna move my frame here. This is non-blocking. It means it doesn't block the next line from going. This is called blocking. Can I have a mixture of both? Verilog allows you to have a mixture of both. Can I easily synthesize with a mixture of both? No. So as a matter of fact, in reality, you should never ever mix them. And here's the fun part. Some of these work in some cases and others in others. So I'm going to try to give you the basic rule that's on here. When you're doing a flip-flop, you want non-blocking. And when you are doing combinational, you generally want blocking. Let me specify why these problems come up. Right? So imagine for a sec, and this is not necessarily the best thing to do, but imagine I had a module and I created a combinational logic piece in here. So let me just do an old Verilog style, always add star, and I wanted to say that y is equal to non-blocking assignment A. Y and B. All right. So, and obviously I need to begin end here. Okay. What does this synthesize? What does it build?
Three separate magic bits.
Okay. So it's going to do these separate, but they're all going to Y. So what does this actually mean inside of Verilog? Creates time zones, right? Or time regions within it. And there's a before and an after, right? And so I've got a Y before and a Y after that's going in here. And so this one says, the first one says that Y after is equal to A before. And the next one says Y after is equal to Y before ANDed with B before. And this one says Y after is equal to Y before ANDed with C before. Right? So what happens?
Last one or by first two.
That one happens, the other two get blown away. When you go to synthesize. Right? So it infers a memory latch, because now it needs to know the previous version of Y. This is kind of an oddball statement, right? If you looked at this and I said there's memory here, right? You would think I'm crazy. Right? But there it is. It takes this last one. I've got the before going to the after, so it's got to remember the last state. But that last state is instantaneous. So you can't build a flip-flop. There's no edge to trigger off of. There's no set time period. It just has to remember from the last instant. So it just leaves it wide open. It's basically a delay, a little latch that feeds it back, right? There you go. That's kind of an ugly circuit, isn't it?
So why is that gonna be the last one?
Right? Because when Verilog goes through, they're all technically at this happening, quote unquote, concurrently. So, but when it walks through them, it's got to have some ordering. Now, technically, you could infer the language is ambiguous enough, any of them could run. Right? So you could also imply from this, and this never happens in synthesis. They always take the last one in synthesis. So that's just synthesis tools. It's unambiguous what they will do. In simulation, it could technically pick any one of them. Now it's random. It's called a race condition. Right? And you don't know what's going to happen. Whoever updates last wins. I.e. the slowest one will be the one to do it. So whichever one of these is, these two AND gates are the same. That's a direct wire. So this one will almost always lose because it's going to be very fast as a wire. And these two are almost identical, which means flip a coin, you'll either get the last case ANDed with B or C. That's really kind of scary. So simulation-wise, you get a random race condition. Right? There's a lot of ugliness inside that circuit. Right? What happens if I do this?
We'll just go through.
This happens instantly. So that means Y gets A. So here I get A and B, happens instantly. And then this one will get A and B and C. No ambiguity, no race conditions, no nothing.
Why would you write it like that?
No, it's a stupid way to write it. I agree with you. Right? You should just write it A and B and C. Right? So that was my statement at the start. You shouldn't do it. But I want a simple example that breaks out, right? That shows you that it's going to blow up in your face in the ugliest of possible ways, you know, and it should be perfectly legal. And imagine if these were longer expressions, so you broke it to go on different lines, just to make it prettier, right? You could very easily, trying to make your code look a little prettier, end up instituting race conditions you couldn't have imagined before. We don't like that, right? So if you use what are called blocking statements, which I would like you to think, even though they're called blocking statements, that's the legal one, I want you to think of it as instantaneous evaluation statements. Evaluate at the moment, right? So that will remove, it makes things very clear and obvious. And so that, blocking this instantaneous of things, always works very nice with combinational logic. Because you notice this, in a combinational logic type circuit, no problems. It gave you exactly what you think you should get. And if you were to remove the time clues, inherently it's uncertain what you're going to get. It's some weird timing condition on where it's built. Right? So we really don't want non-blocking assignments in combinational logic. Does that make sense?
Theoretically, what would happen if you were to have just one of them be non-blocking?
Yeah, I mean, if I did one non-blocking, again, so what it's going to do, the second it goes in here, now it depends upon the evaluation circuit. So the technical rule that it's supposed to go through is that it's supposed to walk through these, so you should get that one evaluating. And then this one and this one are going to happen. This one's going to force an after condition, right? And a before condition. And then it'll allow this one to run at that same exact time, right? But now again, you've got some uncertainty that's happening. Because this one, even though it's quote unquote contemporaneous, this one has already copied its values and will wait to the very end to evaluate them. So what it should do is this one should do the Y and C, and then it should stick it in. So if it follows, if they build it the way it's supposed to, you'll just be flipping those two inputs. Right? However, not everybody always builds it as they're supposed to, so you could end up with some goofiness. So it's generally not a good idea to mix them. So proper synthesis rule says if you want combinational logic, you should use blocking assignments. It just avoids the ugliness. Does that make sense? Okay. Now, imagine I now want to build a flip-flop. Here's the fun thing that happens with flip-flops. So imagine I'm doing a flip-flop. Right, and let's say I want, whenever this happens that, A is going to get the value of B. So let me do it with the blocking first. There. What I want to build, I've got two flip-flops, right? One takes A in and outputs B, and the other one takes B in and outputs A. So they're just kind of hooked back to back. Right? D, Q, D, Q. That's what I want to build, right? Output of one comes from the other. Just backwards on. Simple picture, right? Does this do it? Well, here's the challenge, right? So when you look at this, right? I mean, what could be simpler? Huh? But here you go. Both of these happen at pos edge clock. Okay? There are two independent circuits that are trying to evaluate instantly. So let's say, for instance, when I go to actually simulate this, right, both of these are launched at the same time, but the computer is going to run one of them first. Right? But it's not holding the value. It's going to instantly do them. So both of them it launches and says, do this code. According to the Verilog standard, the last one should run first, but it pushes them onto a stack and then pops them off to evaluate. But, in this case, it will take whatever the A's value was and assign it to B. Right? That happens instantly, it's done. Then it goes to run the other one. But B has now been declared to be A. So A becomes A. See where the problem is? Because it instantly evaluates, this one will instantly evaluate and send its answer over, because it's done instantly. So again, you've got a race condition. And the race condition always happens because there is ambiguity about the order. The order ambiguity isn't inside this command now. The order is between these two that are in parallel. And implicitly, these are in their own little separate time domains, and you do have a before and after with a flip-flop. You can't avoid it. It's part of the system. However, if I use a non-blocking assignment, what it does is this says B at the end of the clock, right? So maybe I'll just put end, end of my time period, gets the value of A, I'll just do an arrow, at the start. And this one says A at the end gets the value of B at the start. Any ambiguity? No. Does it matter who runs first? No. You get exactly what you thought. A gets B old value, B gets A old value. And you got your normal kind of nice back-ended flip-flop thing exactly like you pictured. So if you use blocking assignments inside flip-flops, you will mess it up. If you use non-blocking assignments, you will preserve it. That make sense? So now you know the answer to this age-old thing. Combinational logic, blocking, flip-flops, non-blocking. And that is exactly why under. Right? You will see when you go out to work, I bet you at least half the people do this wrong. And you will get, at various times, your simulation won't match what you actually build, or it will have trouble inferring a build even though it's simulated. You know, all kinds of weird stuff happens. Right? You could have a deterministic input, run it a second time, get a different output. Right? So if you, and all you're doing is just changing what type of an assignment statement. This is actually a little bit of a problem in the language, because they really should have just made one, and the machine should infer the correct one in that location. Right? That would have been the nice way to do. They gave you control of it, but that now means you have to handle low-level tedium. All right. A lot of that actually, so people complain about this. This dates back. Verilog is the older of the two languages. It dates from the very early 80s. Right? And it was a private language. And so a lot of stuff was very manual in the 80s when you did, because this is when I started doing stuff, was in the 80s. And the systems couldn't infer as much that were in there, and people were still trying to figure all the rules out and when the problems happen. And so they said, well, look, there's two different ways we could do it. We'll just let the user decide, because there was no consistent way to figure them out, and people hadn't worked all this out yet. Right? Now that we have worked it out, it makes much more sense to make the machine do it, but it was already built into the language by that point, and so we're kind of stuck with it. Unless they decide to do a revision, which, God, I hope they do on that. But there you go. We feel good with these? Okay. So that's what you should know about always ones. Right? They're inferring in that. Let me deal with the wires and the logics and everything else. Right? So in reality, these are still, wires and wedges and that are still technically around. But it's not a good idea to use them. Right? Anybody know the difference between a wire and a wedge in the original system?
Wire was used in cases where a wire would directly connect to things, where the wedge is used anytime you have an always block where it'll be changing.
Okay, so that's definitely where they were using them. And they used them because they didn't know which one to do. Should it hold its value, right? Can you assign it at one instant and then it holds it until you use it? Inside of a program, that's what you mean, right? You have sequential areas. When I had that, y equals a, right? You assign that at some instant in time. I wasn't saying y is always a. I'm saying give y the value of a, and then later on I said, give y the value of y and b, right? There's implicitly some amount of memory that's going on. It lasts to the next instruction. Even if you don't want that memory to be physically built, at least on the way you want it to run the code, you want it to have some amount of memory line to line. That's implicit within when you're writing these things. Right? So should it hold the value or should it not? So this was another one of those very early on challenges. So implicitly, Reg actually had a little bit of a flip-flop action, a little bit of a latch action going on to it. You gave it a value and it held it. And it didn't matter when you gave it. It held it until you gave it a new value. Right? So that's behaviorally how they built it. So they wrote the data type. Now that doesn't mean that's what it inferred. That was just the data type that you were specifying. That's how you wanted to act while you were specifying things. Wire was a special case of a thing called a net. A net allowed you to have, an input side, and then it could go to a whole bunch of different areas, and just whenever you put a value here, it just copied that value everywhere. Right? So, one input, many outputs, and just automatically copy. And you had to continuously do it. That's why the assignment statement had that statement assign. You're saying permanently fix this to something. think of it like solder it to something, right? You're telling it how to do it. The output of a module, when you instantiate it, you gave it a wire for the output because that module was driving it continuously. It was always had an answer, right? You could find out at any instant exactly what that was by looking at the output of that instance of that module, right? So there was no time it wasn't giving you a value. So that makes no sense for this type of a hold for a little bit even to the next program line. It's just constantly being asserted. Right? That doesn't relate to the physical build. That only relates to the simulation and the internal working. Right? So it's not really an efficient thing to make you do because then people think reg means I want memory, right? And wire means I want a wire. It doesn't. It just means how are you using it. So they give us a new data type logic, right? That allows you to do everything you could do with the other ones. So on the ports, you could say input space logic, 3:0. So like on my port area. Right, what would that mean?
Four,
4 bit.
4 bits, right? The larger one is on the left-hand side, right? So my 0 starts at the little end. I start numbering the little end, okay? Logic is you're going to figure out what the type is, but it's a, I'm giving you single bits that are coming across this. Just specifies more the value range that's going in. That's the name of it. What does input tell me?
And then
You can read its value, but you can't write to it. If you think in terms of this original setup, you don't get access to this. Right? What does output tell you?
you get access.
You can put things to it, but you can't read from it. Right? So if I had in here also an output logic, let's say it's just 1 bit, Y. It's going in. That would mean you could write to Y. Let's say right here, Y equals A. That's legal, assuming A is defined somewhere. Is this legal? Still writing to Y. Why?
these are taking,
Y can never appear on the right-hand side. Fred can never appear on the left-hand side. Y can never appear on the right-hand side. That's what it means. You put it in, it's a black hole, it's gone, right? This one gives you, won't allow you to give back. This one takes, won't allow you to get anything back. Right? Is there any other options?
Good.
What's it called? Right? In-out is bidirectional. That's for buses, because sometimes you've got a port that can go either direction. Right? So that's the other standard port direction. So those are the big three. But notice the nice thing, I don't have to play with those stupid reg wire problems and anything else. It all goes away. Okay. We feel good about those?
is there other things besides logic that are,
So we're going to, in addition to logic, we'll also use integers,
oh, okay,
right?
yeah.
That's used, we do those for when we're declaring variable, like in a gen var statement or things like that, right? We need integers. We'll also have try, right? For tri-state gates. There's actually tons of different data types. So these are probably the most common ones we'll deal with. Okay. I think that covers those ports. Local declarations, those are good. Is everybody familiar with local params and params in general. When you declare a module, in addition to the ports, I can also have parameters that you pass to them. They come just before it, right? And they're kind of fixed values you pass to them, right? And you can either specify it as a param, right, for param or parameters, or you can specify local params. Parameters are ones that can be set from the outside when you're passing them to them. Local params are only accessible interior. Okay? Now, technically speaking, just before the ports list, I can put a parameter list, and I can put some params and some local params. And local params are usually somebody gives you a number and you have to calculate something off it. Like, let's say, for instance, somebody tells me they want a 10-bit number, and I might want to know how many options does that really mean? 2 to the 10th, right? So I might want to say local param, you know, addresses or max address equals, you know, 2 ***, and then whatever I call the exponent, right? So that's in the language. Unfortunately, Xilinx did not implement local params in the list. So it's in the language, but they just didn't build it. So if you were to use a higher end package, but this is the most common package. So the language specifies that you're supposed to be able to do this, they just didn't do it. So if you see code that uses local params doing calculations before the ports, realize yes, that is legal, and no, Xilinx won't do it. Right? You can still use local params inside the module. Those are perfectly legitimate. Right? And that distinction is made so you can have the resulting calculations after it. You just can't do it in the parameter area. Does that create any problems? Creates one. If you wanted to use that local param inside here, right? So say they told me how many, the parameter they were passing was how many inputs to a mux. So they said 8, right? And I wanted to deduce the maximum address bit, which would be 2 :0, right? So I want to deduce 2, so I would take log base 2 of it. I can only calculate it after the ports have happened. So I couldn't use that in the ports area. So if you want to use the local ports, that's why the language spec says you're allowed to do it in that parameter area. So it might make more sense for somebody to say, I want, you know, a 1 to 8 mux or something like, you know, somewhere where I specify the number of inputs. Well, you know, to specify the address bits ain't happening. Right. So if you want it to happen inside there, they have to calculate the external and pass it to you. Or you have to put the calculation in every location, which I hate. The language technically covers it, so it's not a Verilog problem, it's a Xilinx problem. So hopefully at some point, when they switch to Vivado, this is one of those things we've been hoping they'll put in and fix. I haven't seen it get fixed yet, but that is theoretically out there. So just realize if you ever see any of those, that's just a problem inside Verilog system, or sorry, inside Xilinx's system. Okay, so I think we've got all of these. We talked about the assign statements also. Those are single shot ones. And instantiations. So instantiations are any other module being built within you. You can make multiple copies of them. The only difference is what you're passing to them. Right? So if you think about it in that sense, I'm either telling you how to build something using an always. I'm instantiating something, which means I'm telling you where the blueprint is to build me one and how to hook it up. Or I'm doing an assign statement. I'm just saying, real simple build, here you go. So everything you're doing is building stuff. There's no regular sequential code. And that's what creates the problem to people. And that's where these type of misunderstandings can come up. So hopefully now we know what to build and why, at least language-wise on the constructs. We feel comfortable with some of these? Yeah.
Yeah, so System Verilog has also synthesizable set, and the set used only for verification. I'm not sure if Xilinx IDE support like some of the new set, like always combination, like packed array, something like that.
Yeah, so when you get into some of the packed arrays and stuff like that, the more that it gets into synthesizing tools, the less they support. Their biggest concern as Xilinx is to be able to synthesize FPGA stuff. So if it doesn't directly support building an FPGA, or what most people do in it, they're not building it. They're giving you a free tool, right? And since it's free and they're the biggest company, it's the most common used one. For a long time, they were doing their own internal thing called Webpack, and it had really bad support of simulations. So then they went to an external company to try to improve it and pay the tool because they're just getting enough money and people are complaining that their tool stunk. The reality is if you want a really high-end tool that's going to support a lot of those things, getting into some of the packed arrays and things like that get to memory efficiencies and inference, you're better off actually using, so Xilinx Vivado will actually allow you to offload things. Like you can say, for the simulator, use this other thing. Right? My personal preference is there's a company called Mentor Graphics out of Oregon. They're very high-end, they're really nice stuff. So they have a thing called Model Sim. Right? Model Sim is beautiful in its implementation. It's a little more complicated to learn, right, as anything that gives you more flexibility and more power is. But once you get used to it, it's beautiful. And as you're at a university, you can actually download a student copy for free. And we do actually have a license of it. I'm not going to use it standard in here because most of the time we don't need those tools. But if you're like, I'm really into digital design and I want to do this, I'd recommend there's several different tools that are out there that are real high-end tools. I'd recommend looking at a couple while you're still a student to see which one you like, because they almost always have free student versions. That being said, there's no guarantee your company will pay for it. So the reason why I've always stuck with Xilinx's thing is because when you go out and work, you're guaranteed the company will let you have the free standard tool. Right? And if you learn how to use a really cushy tool, it's very painful going back to a non-cushy tool. Right? But if you learn how to use the other one and you kind of have some familiarity with a nice tool and you get the nice tool, then you're like, oh, right? Yeah. It's like being used to driving a beat up old car and then somebody buys you a brand new Lexus or something, right? It's straight upgrade, right? So that would kind of be my comment on that yes, they don't implement everything and they probably won't because there's just no monetary incentive for them. Any other questions? All right, so hopefully this gets you up to speed. We'll do a little more on these type of areas to cover certain specified spots because I want you, when you walk out of this, to know how to build things well. Oh, cool. See you all next time.